this, I guess, the first day of week 6, talking about muscle length and force production. Okay, so if you remember from last video, we talked about several things that affect force production: autogenic inhibition, the biomechanics, agonist and antagonistic muscles, rate coding and recruitment. Last thing that we're going to talk about is force production, or muscle length and force production. And so we've got 4 objectives for this. Now, if you remember back to anatomy, there are several different types of muscle structure. Okay, we've got parallel, fusiform, pennate, convergent, circular, and bipennate, multipennate. And really what we're going to focus on right now are parallel and pennate. Okay, and so it's really important to know that the structure actually affects force production. Okay, and so we get back into physics and biomechanics here, and I'm going to try and simplify it. Okay, so we've got this formula over here, and don't worry, I'm not going to ever have you use that or anything like that. But what I want you to remember or know is that if we increase the angle of pennation, that's going to reduce the amount of force a muscle fiber can generate. Okay, so if a parallel muscle fiber, so one that runs this way, right? So here are a bunch of muscle fibers running this way. An individual fiber going, so here's my muscle. Don't know why it's green, but there you go. As opposed to this muscle, these fibers are going to generate more force than these fibers. And I'm talking individual fiber. However, there is a benefit to having this pennation. And the reason being is that I can pack more fibers into a volume. And so as a result, when I have a pennated muscle fiber, I'm going to have more fibers. And so it makes up for the fact that those individual fibers produce less force. Okay, what we're doing is we're increasing that cross-sectional area. Okay, so just to recap, an individual fiber that's pennated or at an angle will produce less force than a parallel fiber. However, if we're talking about a muscle, a whole muscle, a parallel muscle will produce less force than a pennated muscle, because the pennated muscle has many, many more muscle fibers. It's got a greater cross-sectional area. Okay. Now, the other thing that's important to know is that short fibers produce a lot of force. Long fibers can produce more velocity. So let me say that again. Short fibers, great force. Long fibers, great velocity. Okay. So hamstrings can produce a lot of velocity. They're longer. Quadriceps can produce more force. Okay. Your dorsiflexors, they're long, and so they can go fast. But your plantar flexors, they're short, but they can produce greater force. Okay, so the length determines velocity. Long, fast velocity. Short, slow velocity. Long, less force. Short, greater force. Okay, and so this comes back to the force-velocity relationship, and I show this slide in 220. And so if we look, we've got force on the x-axis here, and we've got velocity on the y-axis. Now notice at our greatest force, which is here, right here is our greatest force, we have the lowest velocity. And up here where we have the lowest force, we have the greatest velocity. Just think about like a bench press. When someone's maxing out a bench press, so they go and they bench 255 or whatever. I don't know. Me, I'll be lucky if I can do 100 these days. Okay, but they do 255. That's their max. And so they're like, I'm going to try 260. Well, they're going to get to a point, let's say they don't do it. So they're doing 260 and they're benching it and they're pushing it up, and then all of a sudden that bar stops moving. Okay, at that moment when the bar isn't moving anymore, they're generating the greatest force. Okay, and then hopefully someone's there to prevent the bar from caving in their chest. Okay, whereas if I just had someone laying down on the bench and then did a bench press just using body weight, they can go really, really fast because there's very little force there. Another thing that's important to consider is lengthening and shortening. Okay, and so if you look, we can shorten a lot faster than we can lengthen. However, we produce greater force when we lengthen than when we shorten. Okay, and so what this is essentially stating is the force of a muscle, the force a muscle can create decreases with increasing velocity. Okay, and that goes back to what we just talked about. So when I do an eccentric contraction, It's going to be slower than a concentric, but we're going to be able to generate more force. Remember, with a concentric contraction, we're producing force. With an eccentric contraction, we are resisting force. Okay, so two more things here is the relationship between force and length as it relates to muscle size. So a large muscle with a greater cross-sectional area produces more force at the same length than a muscle with smaller cross-sectional area. And this goes back to what we talked to at the very beginning of this lecture, right? A parallel muscle has those individual fibers produce more force because there's less cross-sectional area. The muscle itself produces less force than a pennated muscle because it has greater cross-sectional area. So more cross-sectional area, more force. Okay, and as you can see here, the length of the muscle affects that because it affects how many cross bridges are being created. But at all points, a larger cross-sectional area produces greater force. Okay, and then the last one that I want to talk about for this one is that a long muscle fiber produces force over a greater range of lengths. And this should make sense that if I've got a muscle that's a lot longer, it's going to be able to be longer. It's just going to have a bigger range at which it can do things. And as a result, it might affect how or it delays or lengthens out. I hate using the word lengthen so many times, but the force production just is stretched out. Okay, so longer muscle fibers can produce force over a larger range of lengths. And so that's where we're going to end this first day's worth of lectures for week 6.